Assalamualaikum. My name is Nurul Shazana binti Maksobri. My metric number is B0819102004. For this lab 5, I will explain how we construct the simile model for task 1 and task 2 and consult the command for the command window and show the graph for each input that we use. At the end of lab session, I will conclude what we have learned from this lab and obtained during this lab session. For this lab, we use the transfer function real, which is this is the output, this is the input for this transfer function, and this is the real system function. There is closed loop, and then the feedback is unity. At the second transfer function, we label as real 1. Then we add the additional gain to compare the output. Then we set the step input, setting the step input. Step time is 0, initial value is 0, final value is 1, and then sample time is 0.001. For the clock, we set the dissemination is 10 and the stop time is 1 second. This is the command that we use for this lab task 1, which is K1 is represent to the input gain of 0.5, and then K2 for 3 input gain 3, and then K3 is input gain 5. This is the graph when we plot the graph. The blue line is the step input, represent for step input, and then the red graph is the real, and then for yellow is the real 1. To get the peak value, we take the highest, the maximum peak from this graph. Then to get the peak time, we pick the maximum overshoot peak, which is based on first oscillation at axis. And then for the rise time TR, we use 90% from the final value, and then 10% for the final value. So we take the range for 90% until 10%. For time setting, we have calculated the negative 2% final value to get the time setting near the error steady state. So for the error steady state, we get the difference between actual and desired response. This is the result of the graph that we get for 0.5, and then this is for gain 3, and then this is for gain 5. So as we can see, the higher the value of gain, the higher the amplitude that we get from this graph. This is the task 2, which is the construction for the simile model is also same like task 1, but the difference for the task 1 is replace the additional gain before the transfer function real 1, but for the task 2 we place the additional pole after the real 1 transfer function. The setting for step input, the clock, and then stop time is also same. This is the result that we show in the score. As we can see, the input response is 1, And then the blue line is the real, transfer function is real, which is the underdamped response. And then for the orange line is the overdamped response for the real one. This is the command that we use for this task 2. I use the P2 represent to the pole 2. So we have 3 different poles, which is P1, P2 and P3. So if you want to use the different pole, we just edit the P1, P2, P3 in here. So we can, after we plot the graph, we can get the difference between 3 poles, the different graph between 3 poles. Okay, this is the result that we get from the transfer function with the additional pole. For the pole 1, we get the undamped response, which is this is the continuously. And then for the additional pole 2, we get the overdamped response. And then for the last one, additional pole 3, we get the critical damped response.
Assalamualaikum warahmatullahi wabarakatuh. My name is Lokmanul Hakim bin Abdul Kadir and my matrix number is B0819102997. So today I'm going to explain about lab 5-1. So firstly I'm going to explain our observation on the differences between result with and without proportional gain. So I'm going to show one of the example that we obtained. One of it is proportional gain 0.5. So from here we can see that when we use two systems, which one has proportional gain and one doesn't have proportional gain, so the red one is the one that doesn't have any proportional gain, and the yellow one the one that has proportional gain. So we can see that there's slight changes on there are a few differences, such as the steady state error between the input and real one. The final value also there's changes. Next we have different maximum value. We also have different overshoot and so on. We also has differences on the TS, TP and TR. I'm going to explain more later on. So next one is how significant result obtained using different proportional gain value. Explain to your instructor. Okay, so for this one we can check from the table. So from this table we can see there's a large differences between input 0.5 and input 3 and input 5. So we can see that there's only a slight changes between input 3 and 5, but there's a huge or a large changes between these two and input 0.5. Okay, so we can see that for find the value, these two there's only slight changes, but there's a big changes between input 3 and 5 and 0.5. So the peak value, percentage of overshoot, steady state error, our TR, our TS and our TP. So that's the significant result between all these three using different proportional gain. So now I'm going to explain on analysis on the system from all these three graphs. Okay, so this is 0.5, this is 3 and this is 5. Okay, so for 0.5 we can see that when we add proportional gain 0.5, we can see that the maximum peak value peak value, the peak value is much what we call it, lower than the one without any proportional gain. So that's a good thing. Okay, so there will be no less overshoot on the system. Next thing, the TS for real one is better than real, so this will help on what we call it, the system to approach steady state. But something that is not good is the final value is much lower than real one. I mean real one is much lower than real, and the ESS for real one is much bigger than real, so we can say that it's not that steady for we use proportional gain 0.5. Next, I'm going to explain on proportional gain 3. Okay, so from here we can see that the peak value for real one is much higher than real. Okay, so we can say that the overshoot is much higher than what we call it, real. Okay, the TS also there's not that big changes between real and real one, but the good thing for proportional gain 3, the ES is lower than what we call it, ES is lower than the real one is much lower. ESS for real one is much lower than real. Okay, so that so did the final value for real one is much lower than real. Okay, so we can say that that's a good thing. Okay, that's a good thing because from this we can see that system with proportional gain will have more is more steady when it works compared to real. Okay, so but there's a few things that we can see that the what we call it, the contrast of this proportional gain, because this system, real one system, because it oscillate more than real one. I'm sorry, real one oscillate more than real. Okay, so I'm going to explain more on proportional gain 5. Okay, so on proportional gain 5, it's still the same. No, not the same. It's quite same with proportional gain 3, where the ESS is also better. ESS and the final value for system real one system is better than real. Okay, next, from here we can see that there is more oscillation on the real one part rather than the real. So you can see that the motor oscillate much higher, it oscillate more than the real, and it's not that good for a motor to behave like that. Okay, so from these three proportional gain, okay, we can say that proportional gain 3 is better than proportional gain 0.5 and 5. This is because as we know, the ESS is lower than the real part. Okay, so the final value also is better, it's closer to the input, so we can say that it behaves just like what we need. Okay, and this the oscillation also, even though it's higher than 0.5, but it's much lower than 5, so we can say that it behaves more stable than proportional gain 5. Okay, even though it oscillate more than 0.5, but we can see that the ESS and the final value is much better compared to 0.5. So from here we can conclude that proportional gain 3 is the better performance compared to proportional gain 0.5 and proportional gain 5. Okay, so from our lastly, for our table, this is our table. So we can conclude everything that I explained just now. You can see that we can what we call it, we can choose 3 because the final value is closer than 1 to our input, okay, which is good, even though it's smaller than this, but it's not that far the value. Okay, so for the peak value also you can see that 3 is much lesser than 1.63, which is better lah. Okay, for overshoot also we can say that 3 is much better because it's lesser. Our steady state also is the same, so there's not much changes for both of these. So our TR is the same, our TS also is the we can say almost the same. TP also it's almost the same. Okay, so we can say that 3 is the best because 3 is the best because it has lesser oscillation, which will become more stable when it works compared to 5. And we also can say that the ESS is better than 0.5, and our final value also closer to input, which is better. Okay, so as we know, in order to get our VP, we have to get the higher value for the y part, which is our speed, and TP is for time, okay, where we get this speed value. Okay, so for TS we using this formula, which is 2% of FV, which is 0.0187, and we minus 2% of FV, we will get 0.9641. so this is where we get it, and this is our TS. Okay, so in order for us to get TR, we have to find the range of 90% of FV and 10% of FV, and we minus, and we will get the formula of TR. Okay, the value of TR. So for ESS, we have to minus final minus input, or input minus final. So that's how we get this information to put in our table. Before I end my explanation, I want to make one conclusion. Okay, in order for us to choose proportional gain with a better performance, we have to consider the stability and the sensitivity. Okay, so from this lab, the reason I choose input 3 because compared to input 0.5 and 5, because if I compare input 3 and 0.5, okay, from this table we can see that the steady state of input 3, which is 0.0162, is lesser compared to input 0.5, where the steady state error is 0.09. From here we can see that proportional gain with proportional gain 3 is much sensitive compared to input 0.5. Okay, when we compare between input 3 and 5, we can see from this graph, okay, we can see that the oscillation of proportional gain 3 is much in the transition state is much smaller than oscillation in transition state of proportional gain 5. Okay, from here we can say that system with proportional gain 3 is much stable. Okay, the system is much stable compared to proportional gain 5. Okay, as a conclusion, to obtain good performance, the system need to use proportional gain that can come out with result that is stable and sensitive. That's all from me. Thank you.
Hi, my name is Abdul Mahathir bin Abdul Rahmat. My matrix number is B 08Y910396. Today I will present to you about Lab 5-2. The first question is, from your observation, what is the difference between result with and without additional poles? So from the graph, without additional poles, the system will become slower. As we can see from graph P2 and P3, the time response of the yellow line will take more time compared to the red line. And the time settling for the system also takes more time with additional poles. So refer to the yellow lines with additional poles. The time response will be less than 0.05 until more than 0.1. But without additional poles, the time response will be less than 0.05. At the P3 graph, refer to the yellow lines. The time response for the with additional poles, the time response will be 1 point something until less than 1. But without additional poles, the value should be less than 1. So we move to the next question. How the additional poles affect your system performance? The effects of additional poles for the system performance is the value of TP is increased. At the P1, the value of TP is 0.067, while at P2 is 0.197 and P3 is 5.174. The effect of additional poles to the system is the peak value of the system is near to the final value. As we can see at P2, the peak value is 0.2897 and the final value is 2.885. The difference between these two values only 0.0012. At P3, the peak value and the final value is the same, that is 0.953. As you can see, the time peak with additional poles is increased. P1 is 0.067, P2 0.197 and P3 is 5.174. The peak value for the P2 and the final value for P2 is almost the same, while at P3 the final value and the peak value is the same. Next, we move to the next question. Identify the types for each additional poles. For P1 graph, the system is undamped. The poles are purely imaginary, therefore the system marginally stable and the step response oscillates indefinitely. So, with the additional poles, the system will oscillate definitely, as we can see with at the yellow lines. For P2 graph, the graph appears as overdamped response. An overdamped response is the response that does not oscillate about steady state value but takes longer to reach steady state than critical damp cases. So, as you can see, this is the graph for P2. At P3, the graph appears as critically damped graph. A critically damped response is the response that reaches a steady state value the fastest without being undamped. It is rated to critical point in sense that it straddles the boundary of underdamped and overdamped response. Here, the damping ratio is always equals to 1. There should be no oscillation about the steady state value in ideal case. So, this is a critically damped graph. So we can compare to the underdamped graph. This critically damped graph, it reached to the steady state earlier than the underdamped graph. For the D question, analyze the system performance for the three different additional poles in terms of time response analysis. So the value for P1 is peak value is 1.827 and the time peak for P1 is 0.067, while at P2 the final value is 0.2885 and the final peak value is 0.2897. The percent of overshoot is 0.42%. The error steady state is 0.7115. Time response is 0.83 and the time settling is 0.135. The time peak is 0.197. For the P3 graph, the final value is 0.953. The peak value also the same value. The percent overshoot is 0. The error steady state also 0. The time response for the system is 1.4. The time taken for the system to enter the time settling is 2.49 and the time peak for the system is 5.174. So I will show you the plotting data for the P1. P1 we can show you about BP and TP. For P2 we can get error steady state, final value, voltage peak, time settling and the time response. Time response is 90% of final value minus the 10% of final value, so we can get the time response. At P3 we can get error steady state, final value, time peak and peak value, time settling and time response. The time response also the same, 90% of final value minus 10% of final value. So that's all for task 2 and that's all from me. Thank you.
As a conclusion, for the task 1, based on the data that we obtained, the value of the amplitude of each gain are different. The higher the value of the gain, the higher the amplitude that we get. So, the higher the gain we obtain, the better performance for the system. Then, for the task 2, we obtain the different type of response when reaching the value of the additional pole. The system for pole 1 is undamped response, pole 2 is overdamped response, and pole 3 is critical damped response. Based on the result, the example application for overdamped response is when a process cooker is first brought up to heat, it must be heated slowly so that it does not crack. The heat for the cooker comes from steam, so the steam valve is controlled with the overdamped response, so it is opened slowly and allow the temperature to increase slowly. It may take over and our time to bring the temperature from the room temperature to 200 Fahrenheit. Then the example application for critically damped response is the type of response would be steam heating coil for a jacket type product heater. The jacket type allows the steam to circulate around the kettle and heat the product without touching it. Anytime the steam valve is open or closed slightly, the temperature will be changed quickly. So, we analyze that the overdamped response is very slow response and the critical damp response is loop that respond quickly.